So thank you for the kind introduction, and I'm happy to be here and present to you APIC Leak, architecturally leaking uninitialized data from the memory. So today you're going to see a few things. First, I tell you what is APIC Leak, how we understand APIC Leak, how we control the leakage, how we exploit the leakage, and finally you're going to talk about mitigations, how to mitigate this leakage. So the name is APIC Leak, and if you can suggest something, it's APIC in there. So we actually exploit the advanced programmable interrupt controller, and more specifically, the MMIO interface of that device. You don't need to know what the APIC actually does. It's not relevant for this talk. So here are just a few pointers. So it has a base address where it's physically mapped, so we can use that MMIO address, basically. The important part here is that the configuration says that there's usually 32-bit registers, which are aligned to 16 bytes. So there's a lot of free space in that MMIO region, which is actually not used. And you should not access those bytes 4 to 15. Why should we not access them? Because Intel says so. Intel says that bytes 4 to 15 should not be accessed, otherwise you get undefined behavior or incorrect results. So what do? We simply try it. So here is a POC where we map the physical address to a virtual address space, so we can actually read from it. And then we simply read from the APIC range. So the first register is a defined APIC register. So we can see on the bottom here that we don't get back any meaningful value. That's a defined APIC value, so yeah. But what happens if we access the other bytes? We get something back, and it looks really close to strings. So we read some strings over the undefined memory region of the APIC, but why does the APIC return strings? This doesn't make any sense. So we can now see that these strings in our memory dump, and we have to identify where those strings are actually coming from. So we did a few experiments in the paper to basically pin down where the leakage is coming from. So at first, we tried to keep the data in registers and just do computations with those registers. If we then try to leak the data, we can't see any of these values we know, so we can conclude that the data is not leaking from within the registers. If we go one level further, we have the private caches. Can we leak from the private caches? Unfortunately, no. So the next experiment was then to go the other way around. We take a look at if we can leak data from the RAM or from the last level caches, so the shared caches of the CPU. And also there, we didn't see any leakage. However, we saw leakage when the data is passed between the cores. And we concluded that we leak from the superqueue. So what is the superqueue? The superqueue is the interconnect between the L2 cache and the LLC cache. And we can get, with the APIC Leak, we can take the data that's passed over the superqueue. Due to the construction of the APIC, we can get only not all the data which is passed, since 3/4 of the APIC MMIO regions is actually defined registers. So if we access those, we get back defined values. Furthermore, we also found that we cannot observe odd cache lines, meaning that we can only leak even cache lines. What does this mean, an even cache line? If you think about a page and you number the cache lines on a page from 0 to n, you can only access the even ones. So this brings us to our threat model. So we have now this powerful attack where we can leak data from the superqueue. We have an analogy for that we compare it to an uninitialized memory read in the paper. So basically the CPU forgot to zero out the data before passing it along. However, we still need privileged attacker model, so we're in a privileged attacker model, so we still need root to access that APIC MMO region since it's physical memory. Fortunately, however, there is a threat model where that makes sense, and that's SGX. So we target SGX-enclave. What is the idea of Intel SGX? Is to prevent a privileged attacker from actually attacking your code. So perfect fit for that. How does SGX do that? It has one feature, which is called the transparent memory encryption, and it uses the enclave page cache, for short, the EPC. The idea is that every data you store in an enclave gets transparently encrypted on that EPC range. However, the memory and the pages are still managed from the operating system. So the operating system needs a way in order to control the pages of an enclave. And there's one super special page, the SSA, for context switches that stores register values on if an interrupt arrives. If you think about it, if you're computing and an interrupt arrives, you need a place to safely store register values before handling the interrupt in the operating system, because otherwise you would leak values to the operating system. So now we have a few building blocks. We can already sample data that passes over the superqueue when targeting SGX enclaves. Since we can simply read the APIC range, and as we've seen, we got strings back, we can get different data also back. But how can we target interesting data? How can we force data into the superqueue? And how can we keep interesting data long enough in the superqueue that we can actually leak it? That brings us to enclave shaking. The idea of enclave shaking is to abuse the power of the operating system that it can still control the pages of an enclave. There are actually two instructions, the EWB and the LDO instruction, and I just skip to the animation, this makes it more clear. So we have the EPC cache in here. We have one page loaded in the enclave. We can now trigger the EWB instruction to EWB instruction to get the page to the core, re-encrypt it, and write it back into the main memory. And if you follow the path, you can see how many components of the CPU are actually used in order to get the page to the core. And we can also see that the superqueue is also used there. Similarly, for LDO, we have a different way. We bring the encrypted page to the core, decrypt it, and store it in the EPC. And again, we get the data over the superqueue. But still, we're talking about pages. Pages are quite large. How do you target interesting data on a page? And that brings us to cache line freezing. We don't actually need the hyperthread for the leakage to work. But if you think about it, the hyperthread and its sibling are both components of a core and therefore share the superqueue entry. This means also that the hyperthread can influence the content of the superqueue of its sibling. And we use a theory here that actually zero blocks, also blocks of memory which are all zero, are actually never transferred over the superqueue. That sounds a bit complex, so let's look at an animation here. So we have thread 1, the sibling, and thread 2, the hyperthread, and we have both addresses in there which have the same page offset. And thread 1 now tries to load the secret data to read from the secret data, and the data travels over the superqueue to the private caches and finally gets served to the read. If we now look at thread 2, if it accesses the access gets transferred into the superqueue to the private caches and end up in the read. But we didn't gain anything here because we just overwrote the secret data. If we now use APIC Leak, we just get back our own data. Let's look at the zero case. We again load the secret in the superqueue, and now we access on the hyperthread zeros. And when the theory is right, then these are just marked differently in the superqueue entry. This mark is then resolved at the lower level of the hierarchy and finally forwarded to the read. But if we look here precisely, we see that we have frozen a secret value in the superqueue entry, and that's APIC Leak. And we propose two attacks for the SGX context, which are basically abusing this leakage. So the idea is simply you start an enclave, wait until some secret data or important data is stored in the enclave, and then you use the combination of cache line shaking and enclave shaking and cache line freezing to basically freeze the data and leak it afterwards with APIC. You can repeat this process indefinitely without the enclave even running, since the pages still exist if the enclave is not being executed. And if you remember, we had this super special page, the SSR page, which stores register context during asynchronous events. So the idea here is now that we stop after a certain instruction had a secret value in the register, we interrupt the enclave, bring that value on that special page, and then we use the same technique as before and just dump that page. And let's try it live. So I brought you here something from Graz. So I'm currently connected to Graz. So we have here an enclave, and we can just target, let's say, an interesting instruction in that enclave. For instance, I'm now targeting the VAES-NI key gain assist. That's an instruction that is used to derive AES-NI keys. And we can now see that this instruction is used in the enclave somewhere. And the interesting part here is that in the XMM0 register, it has a key, the key we want to extract. So if I then target simply with if I now build a config that specifies where this instruction is lying in the enclave, I can simply perform APIC Leak and get out the key. And if you don't believe me, here is the source code dump, and we can directly see that these upper parts of the key are directly recovered here. And we can also see that we have a blind spot in there. This is exactly the position where an valid APIC-register is located, and we can never leak the data from there. However, if you think about it, you can always recover parts of the key from different parts. So if I take here a second try, I can also use a different config that also leaks out this first round key. And with this incremental leakage, you can recover the full key. So this brings us to the mitigation side. Since we've seen that this is quite impactful and really fast to perform, we need to fix it. And the embargo lifted on Tuesday, and there are already fixes out there, so no worry. The first fix is generally more a recommendation than a fix. The idea is to disable this APIC MMIO region, since it's a privileged component, and if you don't use it, you cannot misuse it. However, you still need root rights in order to access with the APIC, so there might make sense to remove it. However, for the SGX case, you can just say disable it because you're the operating system. That doesn't make sense. So Intel released a microcode update that actually flushes the superqueue on enclave transitions. However, like always, the general suggestion is that also disable hyperthreading, because these superqueue flushes bring you now nothing if you have hyperthreading enabled and can just read in the middle when the data is still in flight. So that brings me to the conclusion. So we have seen APIC Leak is basically the first architectural leak that can leak stale data from within superqueue entries. It does not require hyperthreading, but it highly benefits from it. And due to the APIC virtualization change, we know that it's only affecting newer CPUs. And if you want to have more information, check out that link. There's a lot of information there, also links to the paper, and thank you for your attention.